hey, John.
Hey.
Hey, thanks for taking the time for this call.
Yep.
So why don't you take a little time and introduce yourself? Who are you and what do you do?
Okay. Yeah, I'm John Schock. I am a principal software engineer here at Microsoft, and I'm a lead for the UEFI firmware development on Surface products.
So for those who don't understand either what the Surface products are or what the UEFI are, what are they?
So UEFI is the Unified Extensible Firmware Interface, which is a fancy word for pre-boot firmware. It's an industry standard, so you can go download it and look at the 2,000-page spec if you want. And it basically describes how to build a firmware that will be compatible with a wide variety of operating system loaders, Windows, Linux, pretty much anything really these days. Provides essentially a set of standard interfaces for interacting with the firmware for boot related stuff. So that's UEFI. Surface products, you can go buy one and have a look at the your favorite tech reviewer site and see what they think of the various Surface tablets and laptops and stuff.
And what's so specific when it comes to developing UEFI? Some of us have probably dealt a little bit with BIOS. So what's the difference between a BIOS and UEFI?
So BIOS is the standard that existed prior to UEFI, and it's pretty x86 architecture centric, and it was quite primitive in some ways. It was written in machine language. Well, it was written in assembly, so there's a one-to-one correspondence between assembly and machine language. But essentially, the developer had control of every instruction that was executed. UEFI is a newer standard replacing BIOS, and its implementations tend to be in C almost entirely. And so it tends to bring in more, software engineering abstractions. When you have assembly language, it tends to be one large program, whereas UEFI is a much more modular environment where you can have modules developed by different authors, pre-compiled, kind of integrated together in more of a systemic way than in legacy BIOS.
What's the biggest challenge when it comes to develop in the lower level of the code spectrum? We all heard about C# and Java and all those modern programming languages, but you're talking about assembly level and low level. What's the main difference?
Well, I think one of the hardest things about that area in terms of development is debuggability and observability. There's no kernel underneath you to kind of help you with memory management. There's no APIs that you can call to, get observability. You don't have logging facilities in the same way. Pretty much everything that you have in that environment, you code yourself, or you can leverage open source existing implementations, but you don't have a rich environment like you do in an operating system for a higher level language, right? So for example, if you want to go read or write a file, then you'd better have a full stack of disk and file system and all of those abstractions in your firmware. And typically you own that end to end in terms of, like, if someone comes to me and says, I can't write this file, I have to go all the way down to the hardware and all the way back up to the shell file abstractions they might be using and all that code in between. Wow. Whereas like in a higher level language, it's like, well, eventually C# is going to call like file : open or whatever the primitive is, right? And then it's the operating system's problem, right? And it either
That's
works
true.
or it doesn't.
Yeah.
And there's not much you can do if it doesn't, except, call up your operating system vendor and ask them what to do about it. So, but in firmware, it's all together. So, that's one of the great strengths too. One of the things I do enjoy about firmware is you get to see the entire system end to end, right? Pretty much for the most part, all of the code that you're running is inspectable and under your control. You have a lot more control over the state of the system and a lot more control over how the overall design of the system works if you're a firmware integrator.
And you mentioned a lot of testing. How do you actually debug when you start coding on assembly level or even C? So how do you start debugging those kind of things?
Well, I mean, the primary thing you need for debug is data acquisition, right? Everything else is convenience. But if you can't get data out of the device to determine what its behavior is in a particular way, then you're kind of stuck. And so in firmware, oftentimes the first thing we enable, if we can, is some form of output. And output can take many forms, right? Obviously, you have nice logging and capabilities via the serial port or whatever. But sometimes you go really primitive, like an LED, right? If you can blink an LED in a pattern, then you have debug output, right? I've debugged on boards where essentially we would write ASCII characters to a single LED by blinking it in a Morse code pattern, right? And this would allow us, like, then we film it with our phone and then go decode what the message was to determine where the firmware is or what state it's in, right? I've also done, bus tracing where we actually attach an analyzer to, a bus that contains, like, for example, in most x86 designs, the bus that is attached to the UEFI firmware is just a SPI bus. And so, fairly standard analyzer can decode that bus. And so what you can do is get bus traces and figure out, okay, what's the pattern of code that's being fetched? But you can also initiate transactions to the bus that provide debug output, right? So you might have some junk address that doesn't actually exist in the part, and the part's going to ignore that transaction, but you can put it out on the bus and maybe you ignore the upper 2 bits, but the other, 3 bytes of that address are, debug data, which you can use then to track the state of the system. But typically, those primitive things are what we use at the very beginning before we have like a more robust output driver. Most of the time, our debug is via like a UART serial port log or something like that, which is much more human capable, much faster to debug. And then once you get more mature, especially once you're into a little bit more higher level code, you can have a full stack debugger of some kind, typically via JTAG, that will give you, step through capabilities for your source. And we do use those, although honestly, we use those not very often as you might think. Our primary debugging tends to be via debug logs, because any of our testers anywhere in the world can save a text file and send it to us in email. And if I can solve your problem with that, then that's much more efficient than having you ship me your device and hook some complicated debugger to it. And so when we design code, we often design the logging to be very debug capable. It's precisely for those use cases where it's like, well, I can't physically touch your system and you don't have the expertise to attach a debugger to it. And so I need you to produce some collateral that I can act on. And so those debug logs tend to be our primary vehicle for most issues. So
you mentioned all of these fancy and cool ways of debugging, but isn't that really the way that hackers try to manipulate or read data from the CPU as well?
Well, I mean, hackers are just developers who have different goals in some ways, right? So a gifted hacker should be familiar with all the same tools that a developer is going to be familiar with, right? And they're just using them in different ways to observe different abilities or mess around with the system. So yeah, I would expect that most hackers, at least at the firmware level, are going to know how to take a bus trace, know how to interpret it, know how to kind of understand the transactions that are going on. Most of our firmware, at least the core of it, probably 80% of it is open source. And so they can even inspect the code, they can go make modifications to it and try it out on their own boards if they want. So yeah, hackers are not just, evil people. They tend to be smart people who don't have a lot of morals and want to make some money, right? And so they have access to all the same development tools that we use. But the fact that they use them doesn't mean that we aren't going to use them, right?
Well, that's true. That's true. But is there a common thing that people are being tried to getting hired from a development point of view and join the dark side, or is that just a myth?
So I'm not sure. I've not seen a lot of that in my own career. But firmware is a fairly tight-knit scenario. Once you establish yourself in the firmware ecosystem, I know a lot of the major firmware players at many of the big corporations, right? And so if you show up on the mailing list and no one has ever heard of you, right? You have a little bit of credibility to establish. And even I don't work often on the open source side. Most of the places I've worked, we've had a team that interacts with the open source. So even if I were to send mail to the mailing list, most of the mailing list would be like, who's this guy? Right. So yeah, you kind of know who the firmware guys are. And I'm sure that there are guys that have, found a way to make some money on the side, but I don't know of any of them. Most people are just happy to write code for a living, right? Let me put it. The other thing I would note is that if you have the credibility to get a job at a large corporation as a firmware developer, you will be well compensated, and probably better than you would by a crime syndicate. So, so just bear that in mind. I don't think the incentives really line up super well for people who have alternatives to engage in that kind of work. So,
well, that's at least something to let security staff sleep well at night. So
yeah.
this is a nice addition to that. But how have the profession of UEFI and BIOS developer changed on the course of the last couple of years? And both the transition from BIOS to UEFI, but as well within the UEFI era, what's changed?
Well, in the legacy era, you had a lot of proprietary implementations. You had a few central implementations. Like there was the old IBM PC BIOS that sort of started the whole business and was reverse engineered, right? And then people built on that. But then you had several companies, Phoenix Technologies and AMI, a couple others that came on the scene. American Megatrends. They were the ones who sort of sourced a BIOS core to somebody who was building a PC. But the BIOS was more primitive, it was much smaller, and it did a lot fewer things, and it was implemented a lot kind of more, the scope was much more narrow, more design specific, like all I need to do is get this thing to hand off to the OS, and I don't have any other purpose in life, right? And so the implementations tend to be fairly more varied architecturally, like large corporations who had BIOS teams would kind of craft their own development environment, and that became kind of the way they did things. So you had kind of a splinter off. Everybody conformed to the original IBM PC legacy BIOS implementation, and there are a couple of specs for that were written in the early, the late 80s, early 90s timeframe that, defined what int 19 was, for example, or int 13. But a lot of that behavior that was relied on by like operating systems and stuff to get loaded was not spec. It was just tradition. Like, well, BIOS has always used int13 as the hard drive interrupt. And so if you want to do disk services, you're going to call int13 with this parameters, and you'll find a text file in some news group on the internet that tells you what those are, right? And because all the major operating systems, that's what they do, all the BIOS vendors conform to those interfaces, but there was no kind of standards agreement on those interfaces. What standards exist was basically people writing down what the gentleman's agreement had been before that, right? So it wasn't really a design system in that way. I mean, it was the original BIOS on the IBM PC that kind of started it, was a design system, but it was very purpose-built for that machine, right? And so UEFI comes on the scene to solve a number of problems. The big ones are that you need a more standard, industry standardized way of doing things if you want to have a wider variety of machine types. And so Intel really pushed UEFI, or EFI as it was then, originally as part of their Itanium initiative to be able to develop boot firmware that worked for both x86 and Itanium. But the larger piece of that was like, okay, now we have a chance to go redesign a firmware sort of by standard from the ground up in the first place. And so you ended up with UEFI. And one of the other things that UEFI does that legacy BIOS doesn't do super well is UEFI provides an environment in which you can run sort of arbitrary implementations from other people. So it makes it easy for peripheral developers, for example, to provide a driver for their peripheral that you can just pull into the firmware and works. So let me give you an example. In legacy BIOS, if you wanted to do like a USB Pixie boot, then you're looking at lots and lots and lots of work to make that happen, right? Because you have to understand the USB controller and then the USB endpoint and then whatever strange network device is on the end of that USB endpoint. And all of that's coded in assembly by different people, and it becomes major pain to come in. And then UEFI, as a USB network device vendor, you can write a UEFI driver and hand it to someone with pretty high confidence it'll just work in their environment because everybody's, conformed to that same standard. So that really changed. That interop was one of the big drivers of the adoption of UEFI. So,
and it's the same when it comes to utilization of mice in the BIOS. Let's sort of say you can only use keyboard, but now it's more common to use both mice and touch interfaces and
Yep.
such integrations. Yeah.
Yeah, much of that is again because of the ease of adding support for those devices in the UEFI framework. Again, if you wanted to use a legacy mouse, like in legacy BIOS, for example, the mouse pointer implementation had to be conformant to like the old PS2 IO port implementation, like port 60, 62, something like that. And so even if you had a fancy USB mouse that could do like full USB transfers of, input reports or whatever, somebody on the host side had to take those reports and then fake out as if it were an old IBM PS2 IO port based mouse, right? And so that's just not a scalable or sustainable architecture, right? If you want to do all sorts of fancy input devices. And so UEFI has a full USB stack with abstractions defined for USB input and output and kind of all that business. And so it becomes a lot easier to implement. I've got this fancy new like 6-axis USB pointer I'm going to put into my UEFI. Well, as long as it can give you an X and a Y, in the format that UEFI expects, you can use it as a pointer, right? So
there's been a lot of development when it comes to or attention to security. How would you compare a BIOS to the early version of EFI and UEFI to the later version of UEFI when it comes to security?
Well, legacy BIOS had no security really. It wasn't even designed to think about that, right? What security it had came from the fact that it was typically read-only, right? So it was hard to modify unless you had the right tools or knowledge of the board design to allow you to do that. And so it did have a little bit of security in the sense that, like, unlike a disk, which is explicitly read-write, the BIOS tends to be read-only, and so it's hard to hack it in the sense of going in and modifying. Now, if you find a bug in it, it becomes hard to fix as well, right? But it was not designed, especially the older ones, they were never designed with the idea of security in mind. Like, securing the firmware was not a design goal for the original BIOSes. UEFI, early UEFI was still kind of in that mindset. Frankly, it's a miracle every time a machine boots. And so us firmware engineers are like, man, we have bigger things to think about. At least we used to. Nowadays, a lot of the architectures of the SOCs and so forth have stabilized. And so we're not just desperate to boot the machine in the same way anymore. So we have a little bit more free time to think about security. And more importantly, the industry and the ecosystem has moved to where security of the firmware is a much more interesting thing than it was 10, 15, 20 years ago. People are much more interested in attacking the firmware. And part of that is the cost of attacking firmware is higher because firmware is, again, read-only. It's got proprietary interfaces. It needs more knowledge to hack than, say, an open source operating system or even Windows. But both the Linux and Windows and other operating systems have had such a focus on security for the last couple of decades that they're becoming much harder targets, right? And people are much more aware of what you can do at the OS level. And so even when you can compromise an OS, it's much easier for like an IT department or a savvy user to be like, I don't trust my machine anymore. There's something wrong here, right? And so firmware has become a much more attractive target because it's in some ways a little bit sneakier. If you can get into the firmware, then you're running before the operating system starts. So you have an automatic strategic advantage over the operating system because you own the machine before the operating system starts. So that makes firmware an attractive attack if you're trying to compromise an operating system that has been hardened, right? Now, if your operating system is weak, like if you can compromise the operating system really easily, then no one cares to hack firmware because it's, extra work. But once the operating systems have been secured, now firmware becomes a more interesting target because it's easier potentially to get at if it's not been secured the way the operating system has. One of the other advantages of attacking firmware, if you're a hacker, is that firmware tends to be more persistent on a device than the operating system does. an IT department can completely wipe a hard drive and put a new operating system with the, standard corporate load on it in less than a half an hour these days, right? You can just walk in and I don't trust my laptop, and the IT guy is like, okay, take a seat. I'll wipe it and put a brand new operating system on it, and then you can trust it again, right? So operating systems, in some sense, once they're compromised, like recovery from that compromise and reestablishing of trust is relatively straightforward for an operating system because you can just nuke it and start over. Firmware is a little bit different because firmware persists on the device. So if you can get a persistent foothold in firmware, it doesn't matter if you wipe the device. It's there forever, right? In some sense. And so in that sense, firmware is also an attractive target, not just from the I get there first so I can compromise the operating system, but also and then I can live there forever kind of standpoint, right? So it is attractive. It's definitely attracting more malicious views than it used to, right?
So, yeah, it's more of the center of that until death.
Yeah.
Yeah. So how do you kind of get out of where you suspect the UEFI to be untrustable? Do you change the motherboard or do you replace the UEFI firmware?
Well, the first thing we've done is we've worked with the silicon vendors. Most vendors support some form of firmware authentication, where the root of that authentication is a key that's actually in the chip, in the CPU chip itself, the SoC. Right. So most vendors support some form of, hey, I'm Microsoft Surface authorized developer. That means I have access to a private key that no one else has of some form. And the architecture varies depending on what you're working with. And that firmware, that key is used to sign the firmware. And if the firmware is not signed with that key, the CPU will refuse to execute it. Right. And what that means is that even a single bit flip somewhere in the firmware code will cause the code to become untrusted, right? Not executable by the CPU. And consequently, you can eliminate a whole class of attacks at that point, right? Because the only compromises you have at that point are the ones that you put in your own code, right? No one can modify your code from the outside with like a firmware programmer or something and expect it to work. Right, because they would have to have access to cryptographic secrets that they don't have. Right. So that gives us a fair measure of protection in terms of tampering. And then it becomes a matter of whether or not we're writing secure code in the first place. Because if you have authorized code on the system, but it still has holes in it, then you can still compromise it. Right. And so for that, we run a number of different strategies on the development side, but they're very similar to what you would use in like a high level, a static analysis kind of stuff, or making sure that certain protected sensitive parts of the firmware get extra review, security review by security teams within Microsoft, those kinds of things, right? Yeah, and so we try and stay abreast of that. And then the other thing is that we do watch what kind of vulnerabilities are being reported in the industry typically. And there tends to be trends. People tend to like to find some kind of compromise and then latch onto it and develop a whole bunch of variants of it. Right. And so you can kind of keep an eye on and be like, okay, it's become really popular these days to attack, this aspect of firmware. And so we should take a double close look at that infrastructure. And sometimes we just say, you know what, we don't need that infrastructure. Like it's not actually doing anything for us and it's just an attack point, so let's remove it. Right. And so we just dispense with it altogether. Or we say, look, this has been a very common class of attack. We're gonna rework this architecture so that these kinds of attacks will actually be very easy to detect or otherwise, prevent. And so we do monitor what's going on in the industry and say, we're seeing a lot of this. Let's go figure out how to harden that component, right? So.
Smart. And if I'm not mistaken, some of the first devices that Microsoft secured via its firmware was the Xbox series. And I've also known that a lot of stuff have been done with the Secure Core PC line of series and family. And do you know how, could you tell us a bit on how that works? Is it like from a chip to cloud vision I've often heard Microsoft talk about, but how does that really comprehend in real life scenarios?
Well, on the Xbox side, I can't say much because I don't know much, right? I can speak a little bit more to the secured core PC, but that's just elaboration on what I just said, where we have a cryptographic authentication of the firmware and some details about how that crypto authorization of the firmware is preserved through the boot. So that we can attest to the operating system, for example, that, hey, we haven't been tampered with and nobody has compromised our code and we didn't run anything that was unexpected. All of the signature of this execution of the firmware to this point where we're handing off to you, operating system, has been cryptographically verified to be correct. Well, maybe not correct in the sense of doesn't have any bugs, but correct in the we didn't run anybody's code that we didn't expect to run. Right. So yeah, so from a secure core PC, that's kind of the goal, is this. I don't know if you're familiar with this term, the root of trust for measurement. So
Yeah, a bit of it.
in the industry, we have the Trusted Compute Group, which is the folks that, develop the specifications for TPM and other trust technologies in the pre-boot and boot. And so a lot of the secured core PC approach is based on those kinds of standard approaches, those trusted computing approaches. And so essentially those feature things like cryptographic measurement of components as they execute into tamper-proof modules that you can then interrogate to see what happened. The TPM itself is hardened against physical attack typically, like it's hard to open it up and scrape out the keys and stuff inside of it. It's hard to tamper with it to modify the signature registers that show what has been executed. And so those technologies from TCG, from Trusted Compute Group, and those measured boot technologies are a core part of what we rely on for secure core PC. And the basic idea, the root of trust for measurement, is this idea that you have a rooted trusted component. It's typically the core chip, like the CPU chip itself. And that root essentially is the first element that you implicitly trust, that you say, I don't have to have verified that this is correct, right? This is chip ROM code that came from the factory that no one can modify, so I trust it. And it starts the first measurement. And so it'll say, okay, I'm going to measure the next component of boot, which might be like, the reset vector or something, and say, I'm going to measure, the module that is going to run that component and store that measurement into the TPM as a hash, right? So now I have a trusted root, which is hardware typically, and then the first measurement of the reset vector is a hash. And then the reset vector will run for a little while and it'll decide to run another component. But before it hands control of that component, it'll measure it into the TPM. And you end up with this chain of measurements, the first length of which is that hardware trust. And then every link in the chain measures the next link, right? And so when you get to the end of the chain and you hand off to the operating system now has a whole chain of measurements that it can review, from a code standpoint and say, okay, I trust each link in this chain. I recognize this measurement. This measurement is known good, right? And so that means the whole firmware has been executed. Now, if you had a malware module come in there and say change one of those components before control was handed to it to compromise it in some fashion, that would change the cryptographic hash of that component and cause one of the links in that chain to have a different measurement than expected. And now the OS can say, aha, I see that the component has been modified. I no longer trust this system. I'm not going to disclose any, encryption keys or secrets that I might otherwise be using, right? The TPM chip itself can also be used to store keys. So for example, like the key to your disk encryption can be stored in the TPM, right?
And other authentication systems like Windows Hello for Business?
Yeah, those kinds of things. And the data for those can be essentially set up such that you can only retrieve that, you can only decode it from a cryptographic standpoint if you can retrieve the key port from the TPM. And the TPM will only release the key if those signature measurements that were done during the boot all line up. You can think of it like a combination lock, where the combination is that you ran exactly the firmware we expected you to run and nothing else, right? And only then will those keys be releasable from the TPM. So even if you compromise the OS and you're like, hey, give me the key, like the TPM will refuse to release it to you because the signature doesn't match, right, of the system up to that point. So
Y-
that's the basis
yeah.
on which a lot of our pre-boot security is based, in terms of making sure that we have a reliable chain of trust from the very, very early hardware all the way up through the operating system start.
We've seen Intel vPro are doing some internal cryptography processes, and we've seen Microsoft Pluton is doing some where they built in their own cryptography circuit into the SOC. What's the main benefit of moving away from the TPM and integrating that to the CPU?
Well, those elements control the same. They contribute in the same way that a TPM does, right? So it's not like a fundamental change in how that works. It's just that now the secure element that is computing those hashes and storing them and protecting them is in the sock itself and not a separate IC, right? So that eliminates a class of attacks where you can, like, sniff buses or do other things to try and get in between the SoC or the chip and the CPU chip and the secure element, whether it's a TPM or whatever. If you put that secure element inside the chip, now you have to have, a scanning electron microscope if you want to, sniff that bus, right? So it hardens against certain types of physical observability attacks where you can see the traffic and maybe make some guesses or inferences on what that looks like. Right. So that's one of the reasons why a lot of these elements are moving into the main SoC, is to eliminate some, physical attack type stuff. Right. So
Yeah. Uh, one of the last things that I wanted to kind of dig down on is the art of artificial intelligence. How has artificial intelligence and tools like the GPTs and coding assistants, how do those kind of both aid developers on a UEFI level, and how do they threaten the integrity of the UEFI for malicious
well,
attacks?
I had one of my colleagues type a question to ChatGPT. It was like, implement me a UEFI firmware protocol that can divide 12 by 3 or something like that, right? And so ChatGPT came up with, relatively correct framework for how to do that, except that instead of computing the result of 12 by 3 to be 4, it came out as 6. That's the answer. so it has its. One of the things that ChatGPT can kind of do is point you in the right direction about what the code might look like, or kind of where to look in terms of how to build it. But it's still not to the point where it can give you what I would consider a reliable or correct solution most of the time, right? It still requires a human to look at it and be like, 12 by 3 is 4, not 6, right? So, and so you have to kind of look at it. So it is handy in terms of, like, man, I need to do some, let's say I need to do some file system interaction in UEFI, and I don't really know what interfaces are available for that. You can go to ChatGPT and say, hey, how do I do file system IO in UEFI? And you'll probably get something that will at least point you in the right direction. But it's not mature enough to the point now where, as a production like developer of Surface, I would trust ChatGPT to write my file system driver for me. Like, it would never work, right? So I don't feel like ChatGPT is necessarily going to replace developers, but I think it is going to enhance the productivities of developers that get familiar with it in some ways, especially if you're a new developer to the environment and you don't know a lot of the kind of the infrastructure very well. It can be a real short circuit to finding out where to look to learn. So I would say that ChatGPT is what I would consider a guided learning tool, but not a replacement for a developer, right? And so I'm not that worried about it in terms of threatening our jobs, right? What it means is that likely my junior colleague who is just starting to work on UEFI firmware and hasn't learned very much yet, he can go ask ChatGPT instead of coming to my office and asking me, right?
So it's more like a co-pilot. We had that peer programming instance where you're supposed to sit two and two to learn the code, to understand the code. So this
Right.
is kind of a peer review of what you do, and then
Right.
instead of bugging you.
Yeah, and it means that, like, I expect over the long term, I'm going to get much more interesting questions from my juniors that I will have to actually think about, as opposed to information retrieval. I know the answer because I looked at that code, 10 years ago. It's probably over here. Search, search, search. Here you go. This is what you need, right? That's what ChatGPT is good at. But like, what is the correct design philosophy to use when designing the security sensitive component is not going to be an answer that I would trust from ChatGPT, right? so I that one, so I think what it's going to do is it's going to make it easier for people to learn the environment better and become kind of grounded in the basic technologies and background. But I don't think it's going to solve the really hard problems, right?
So artificial intelligence won't take your job, but someone
Well,
using
not until I
artificial
retire,
intelligence,
probably.
yeah, but someone using artificial intelligence might take your job.
Yeah. Or at least someone using artificial intelligence to inform their own learning is going to come up to speed potentially faster than someone who is not using that to help guide their own development. I mean, honestly, think about it this way. The artificial intelligence is trying to mimic what human beings have done for thousands of years, right? It still has some work to go before it can match the state of the art in terms of neural network processing, right? And so I think that yeah, it's going to allow you to access information filtered in a way that makes it easier for humans to process and develop their own minds. But ultimately, a human who is developing their own mind still has a strong advantage over a straight AI, right? The AI is a very good supplement to that, I think. But, and this might not be true 50, 100 years from now. I can't predict the future, and maybe these things will be amazing by then. But the current state of the art is powerful, but it's no replacement for thinking, right?
Yeah. All right, John, thank you so much for your time on both BIOS, UEFI, and artificial intelligence and whatnot. This was super interesting.
Yeah, I'm always happy to do it.
All right, thanks. Bye.